Any day. Okay. So what this is I just programmed up a spreadsheet to use this little formula that the distance array goes is minus 1 over beam C log of the uniform 0, 1 random number. And then you can change the beam C value here, it's 2. And so then, like, here's the theoretical distance, it's 1 over beam C is 0.5. Here's a sample mean distance. Here's a sample standard deviation. And what I did here is I've just used the little formula, and I've got like 10 columns here that you can generate numbers, and you'll see what comes out over here. And the way you generate a new set of numbers, at least on my computer, is with Excel. If you hit function or hit the F9 key, you can see it's generating here a new set of random numbers, a new set of distances using the formula, and then for this set of distances, here's the mean and the standard deviation that you can just play with there. And so does that seem to work on everybody's computer? If you hit F9, it generates, and I have no idea how this works on a Macintosh. Maybe the same, maybe Macintoshes don't even have function keys, I don't know. Anyway, so you can play with this, and you know, on the instructions I've just got a few simulations to perform here. And also down at the bottom here, there's a couple of plots where here, this is our little 1 over beam C log random number formula in red, and then for a particular realization, these are the points that were actually being generated. So here's the distance from 0 on up, and then this is just the distance plotted times the trial number, that is which random number was drawn. And so you can just sort of see the spread there. So if you hit F9, you'll see those numbers bounce around. And so nothing profound. You know, here's one where it seemed to generate a lot of kind of low numbers, and they were all less than the expected average value. And then you try another set of 10. Well, here's some where there's bigger ones. And, you know, they just bounce around. So anyway, the only thing this does is kind of give you a feeling for the spread of distances that rays will go before they interact. So anything from, in this case, almost 0 out to 1.2 meters, and a bunch of them around kind of 0.5. So there's a couple of little exercises at the bottom here just to play with this. You can just hit the button, generate a bunch of new things, look at how the mean distances go. And of course, in theory, if we go up here a little bit, in theory, for a beam C of 2, you're expecting to get 1 over C for the distance and 1 over C for the standard deviation. Well, here's 0.52 versus 0.37. You know, here's another one, 4845, 0.27, 0.17, really low values, okay? And here's some more, you know, just play around with these. There now we're really big values, 0.8s. So, you know, on average, you ought to be getting this 0.5. And so anyway, you can just play around with that with this spreadsheet. And then there's another one that's a little fancier.
On Apple, the recalculate is command enter, or command equal sign.
Okay, so command equal sign on Apple. Good to know. All right. Then there's this one called error propagation. So we fire this guy up. So here, what I did, let's get over to where I can see things here. Okay, on this one, we sort of briefly mentioned this thing called the quasi-single scattering approximation, and it says that RRS is basically BB over A plus BB, and then there's actually a factor that involves the scattering phase function, and here we have the sun's over here at some theta sun value, so that light gets in the water and it's being scattered back upward through this scattering angle, and then we're getting an LW looking straight down, which is what goes into RRS. So there's actually a phase function thing that's from the solar distance into the distance looking straight down. Actually, it would be minus 180 degrees, because in my coordinate system, that's the light going straight up. Anyway, and then that's actually divided by the backscatter fraction, which some people call B and some people call BB tilde. There's that, and then there's a 1 over 1 plus cosine of the solar zenith angle in the water. So here, if I've gotten the sunlight into the water, this is the solar zenith angle in the water. Well, anyway, that's what this quasi-single scattering approximation says that RRS ought to look like to the first order of scattering. So I just broke this thing up. I programmed in this little formula, and so I put in, let's say we try A as 0.1, BB as 0.007, this little factor in the middle here was 0.11, and say the sun angle was 40 degrees. And then I said, okay, if you take these numbers, you plug them into this RRS formula right here, which is right here, you would get that RRS is 0.0041 per steradian. Fine. Now, come along and say, well, how good is my absorption value? I don't know, maybe it's good to 20%. If that's the case, then you could write that absorption would be 0.1, and if we assume the errors are normally distributed with a standard deviation that's 20% of the mean, that would be 0.1 plus normal of 0, and 0.02 is 20% of 0.1, or you could just write that as A is normally distributed as normal of 0.1, standard deviation of 0.02. Ditto for these other things. And I said, well, okay, maybe for the sun angle at 40 degrees, maybe I'll just play like it's equally likely to be anything from, say, 35 to 45. So there, instead of a normal distribution of errors, I just said let it be equally likely to be anything plus or minus 5 degrees. So then I programmed up the little formula where I put in the AB, the phase function factor, the sun angle, and then the standard deviation of the errors, or the range on the sun angle values. So here would be plus or minus 5 degrees. You can change those numbers, and then when you do another run, it actually computes 1,000 values here. So it's going to take the 0.1, that standard deviation, draw the random number, etc. There's what that absorption looked like, the next one, the next one, the next one. Same thing for the backscatter coefficient, the phase function thing, and the sun angle. It plugs all those in and gets an RRS, and then you can look at the distribution of the RRSs that were computed from these 1,000 values. And once again, if you do another, F9, you can see it's recomputing all the numbers here. And then out here is the mean of the 1,000 runs and the standard deviation. So here it's 0.0042. In theory, we got 0.0041. So you can kind of play with that, and then you can generate, wherever it went here, you can generate from those 1,000 values a histogram of the frequency that you got, say 0.003 to 0035, 0035 to 004, etc., and get a little histogram of the deviations there. Now, I can't figure out how in Excel to get it to update the histogram when you do a new set of numbers. If you know how, let me know. But basically, there's instructions on the back that are at the back of the thing here. To generate histograms in Excel, you have to install their data analysis package. And that's apparently there, it's just not activated. So there's little directions how to, go browse down, pick this data analysis tool pack it's called, click the button, say activate it, and when you do that, then up here you will see a little data thing, and there's instructions on how you can then come over and like block out your 1,000 RRS values. You go into the data thing, you go over to data analysis, you pick histogram and OK, etc. And then you have to put in the input range, like what sizes of bins do you want. And I put in here a range of bin sizes, so you can just copy those over, use those as the bin ranges, use RRS like E27, E to 1026, will get you all 1,000 of these, pick those guys, stick them in there, click the button, and then what it does is it generates a histogram on a new page out here. And it looks like you have to generate the new page for each new histogram. So efficient. Anyway, maybe that's just because I never use Excel that I don't know how to do it, but like here's a histogram here, and I guess that's the only one I've done. So anyway, just play around with this and maybe generate a couple of those histograms, see what they look like, and then there's a thing that says, well, okay, we're getting, like in this example histogram, that's like a plus or minus 29 or 30% spread of values. So if we come down here, the theoretical value is 0.0041 here, but if we kind of go from say here to here, that's sort of plus or minus 30% with some outliers much smaller and bigger. Well, suppose now you say, I really need to get IOPs and sun angle so I can put them in Hydrolite and get RRS that is guaranteed to be, say, plus or minus 10%. Okay, so how good do your IOPs have to be? Well, you can come up here, and right here you can keep the IOPs, but now instead of assuming that the error is 20% in absorption, maybe make it 10%, and so on with the others, and play around with decreasing these things until you get an RRS that's good to say plus or minus 10% or 5%, whatever you want. And you'll find out that these have to be pretty accurate measurements to get the RRS distribution really accurate. And so just play around and see what you come up with there. And then the last part, and also I don't know, when you copy over my spreadsheet where I've used this data analysis package, whether that carries the data analysis package with it or not. Probably not. You probably actually have to install it on your version of Excel and then bring in my spreadsheet. But anyway, call Microsoft with your complaints about that. Then there's a backward Monte Carlo 3D code student version. So what's in there, if you look at it, is this. There's an executable. And this guy was compiled only on my laptop under Windows, so it'll probably only run under Windows. But here's the geometry. And this is also in the handout here. Basically, we have the water surface. I have this funky coral reef that looks like this. So that's all coral reef. So when you run the code, you'll put in, this is the top of the reef, Z top. It's going to have some reflectance, R top. And my coordinate system is right here. So this is x equals 0, and z is measured downward. So you'll put in like z top, if it's 20 meters, that puts this top at 20 meters deep. This wall is always at x equals 0. And then you're going to put in the reflectance of the wall. So that might be like 0.05 if it's 5% reflectance, or you could put in 0. It's an absolutely black absorbing wall. Now, the first things are to just say, well, does this code agree with Hydrolite? So put a sensor out here. Let's say, and I'll do a run in a minute and you'll see how this works. But we might put an ED sensor at, say, Z of 10 meters. And if we put this, say, a couple of 100 meters away from the wall, then this wall is just going to be way over there. It's not going to affect our answer. So we could put here, actually the X of the detector might be plus 100 or 200. We can set Y equals 0, and maybe we set the depth of the detector, let's say at 10 meters. And we'll pick an ED sensor, EU, whatever we want. So we're really over here now, a long ways from the wall. It's a one-dimensional geometry we can compare with Hydrolite. Or if you put the sensor way back here, let's say we had here an LU sensor at the detector of minus 100, 0, let's say plus 5 meters, and the top here was at maybe 10 meters, then you're simulating one-dimensional shallow water with a detector at 5 meters in 10 meters of water, etc. And you can compare those numbers with Hydrolite. Then when you get into this area, this wall, there's something here, there's nothing here, you start getting a 3D light field. So anyway, there's just various simulations there. The geometry's all there. And so let me just show you how to do a run here. If we fire this guy up. Okay, so it just comes up and it says, do you want to, there's a whole bunch of input values, which to start are just kind of generic things. When you get to the end of the run, you can say overwrite this file, and then those values will be there next time. So to start with, I've just called this file defaults for the wall. So let's say, yeah, that's okay. We're cool with that. You can now put in some root name that will identify the run. So we can say, no, we're not happy with that, and call it test 1 or something, whatever. You'll see how that works. Enter. And then you can put in, just like Hydrolite, some descriptive title. So if I'm not happy, I hit an N and get no and say example run 1, let's say. Okay. So it's taken the root name, generates a file called printout test1.txt. There's also going to be a file called table test1.txt we'll look at in a minute. So yeah, we're happy with that. And you can, to accept it, you can just hit enter. You can also hit a Y. And so now it says, okay, the coral wall reef parameters are the tops at 50 meters, the reflectance is 0, the wall reflectance is 0. Okay, so for the first run, let's just take that. If we don't like those, we can say, no, I don't like them, and it'll say, what do you want for the new values? Well, let's put the top at 20 meters, the reflectance is 0.05, and the wall reflectance is 0, let's say. Okay, then there's a thing that says, how deep do you want me to trace a photon before I forget about it? So I have it as 100 meters. So the idea is I'm going to put a sensor over here at, say, 10 or 20, 30 meters deep. If some way a photon makes it all the way down to 100 meters, the chances of that guy getting all the way back up are just about 0. So I just say, if it gets to 100 meters, throw it away and start over. Then you can change that to whatever value you want. Then default detector location. So here I've got is 200 meters to the right of the wall, Y is 0, and the depth is 10 meters. So let's just go ahead and take that. Then on the nadir, or the direction the detector is pointing. So the nadir angle, it says 180. So that means theta is 0, is the detector is looking straight down. That would be measuring light going up. If the detector is looking straight up, which is 180, then the light's going straight down. So if we want to simulate ED, then you put in the polar angle of 180, it's looking straight up. If you want to simulate LU or EU, point your detector straight down, but you can point it in any direction you want. And then the phi detector is measured, if here's the reef wall, this is phi equals 0. So like out here would be the detector looking towards the sun. If the sun's over there, looking at right angles parallel to the wall is 90 degrees. Or if I pointed the detector at 180, it's actually looking right back at the wall. So that's the way the geometry works there. So let's just go ahead and take those values. And then there's a choice here for what kind of detector. And I said, well, a planar radiance detector. Now, if you want something else, you say no, and you could pick a Gaussian tube radiometer, a TSRB sensor. It actually has the response of the TSRB built in. You can get a cosine detector, an E0D or E0U detector, or a full scalar detector. So you can pick whichever one you want there. And let's say we pick that we want a radiance sensor, that it asks you for the new value of the field of view half angle. So that simply means I've got my radiance sensor and it's looking out here at a field of view that's, let's say, 5 degrees. That's the half angle. So you can specify a narrow angle, wide angle, whatever. So we could put in, let's say, 5 degrees. Okay, then you can put in IOPs. This is just like the constant IOP model in hydrolite. You're going to put in A, B, and pick a phase function. So let's just take those. You can pick Petzold. If you say no, it'll give you a list of phase functions. You can pick one. The wind speed, 5 meters per second. Now, in hydrolite, you have to put in where you want the sun angle. In this guy, it's going to do all of those sky positions in one run. So it just kind of tells you, you know, all you can pick is, do you want the semi-empirical sky model or the idealized? And the semi-empirical model is basically the same one that's in RadTran. So let's just, for the moment, we'll just pick that one. Say it's okay, cloud cover 0, and then pick a wavelength, which would, just like in the constant IOP model, this wavelength should correspond to the IOPs, and the sky model is going to use this to get the sky radiances at the wavelength of the IOPs. So let's just go ahead and call it 400. And then here it says, how many rays do you want to start? What's the seed for the random number generator? And how small does the weight have to get before you throw it away? So, okay, let's just pick 50,000. And, you know, the best way to generate random numbers is like let your cat walk across the keyboard or something. And, you know, you can also just go like that. But anyway, so let's just take those values. And then it says, do you want to overwrite the old defaults file? Sure, might as well. And it runs. Bingo, away we go. Now with only 50,000 rays, whoops, the next thing I need to tell you is if you just click on this, it'll run and then the window closes. Well, that's useful. So I always start the command window, go to AA main, 2019 class, let's see, and then I look in CD to, I guess it's, and then there's the run directory, whoops. Okay, and so then here's the code we were running. Now, if you go here and just issue the command BMC3D SV, then you'll run the code and the window will not close. Okay, so now let's just go through here, and since I saved the output, it's all there. And now it runs. And then you get out here a little table of values. So there's some checks, and then there's a table, and it says for the theta of the sun, the phi of the sun, here's the estimate, which in this case I was doing a radiance, so there's the units. And how many quads did the sun get, or how many rays did the sun quad get when I did this simulation and I moved the sun around? And then here's the ED in the air that was onto the sea surface. A little rule of thumb, which you'll learn, is that when I'm doing this backward ray tracing, that whatever the quad, the little theta phi box that has the sun in it, needs to get at least 1,000 rays, preferably 5 or 10,000, in order to get pretty small amount of Monte Carlo noise. Well, you can see here, if let's say the sun was at 40 degrees and a phi of 0, I only had 233 rays. I estimated this radiance was going to be 8.9 times 10 to the minus 2. Okay, play around with this, trace more and more rays, this number will go up. And here, if I'm out in that one-dimensional area away from the wall, really every phi value is kind of an independent estimate of what the radiance or irradiance would be, because it's not seeing the wall back there. So here, actually, all of these numbers are really independent estimates of this LU or whatever it was I was estimating. And so you can just kind of look at from 0 around to 345. You really have 24 values there that you can use to look at the spread of the estimated values. Okay, and I spell that out in here. So anyway, you get that, and then there's a little just table here that says we started 50,000 rays. We actually had 2.5 million rays were traced to completion. That means each little multiple scattering path counts as one more ray. So there's like 2.5 million actual rays bounced around compared to the 50,000 I started with, and 45,000 went through the surface up to the sky, got tallied, and there's a bunch of other things, and sometimes a ray will go berserk and it'll get anomalously tallied, whatever. And that was 5 seconds of runtime. So there's also, to take a look here, there is an output file, and the run will put a printout file and a table file. And the printout file just basically documents, all the inputs to the run, all that, just kind of like looking at a hydrolyte thing. And I've just built in things like the water index refraction and various other things you don't need to look at, like the sky grid partitioning is the same as in hydrolyte. So there's all of that stuff, and then there's some info on the phase functions, the atmospheric conditions, etc. And then finally you get the same little table we just looked at right there, and then also this table thing is just the table of values. So if you want to just open this up in MATLAB or Excel or something and play with it, it's just a little quicker than looking at the whole printout thing, but it's the same information. Okay, so that's the way the Monte Carlo code runs, or hopefully will run. So anyway, the first thing to do was do a hydrolyte run and get numbers that you can compare out here, then do some Monte Carlo runs and see how those numbers compare to the same hydrolyte number. And I actually, in the directory here, I have This is the printout for the Monte Carlo lab base run. There's my hydrolyte run where I used the constant IOP model and got, down here, if I look at, these kinds of numbers here or the ones down here, I'll get numbers that I can compare with the Monte Carlo code. So you can do that one first, and I just copied my output here, and then just do various little runs here. And then the last simulation said look at 3D effects of the light field. So there, if we say put the coral top maybe at 10 meters, and we're going to have a wall here that's, let's say, 0.05, 5% reflectance. And then suppose you put a sensor here that's maybe an ED sensor, and it's only 1 meter away from the wall. So the X of the detector is 1, Y of the detector is 0, and then the depth of the detector, let's say if we put the wall at top at 10 meters, maybe put the detector at, say, 30 meters. So then you do a run, you get the ED values. Then move ED out to, say, 2 meters, 5 meters, whatever, maybe out to 20 meters. XD is 20. And you'll see how, like, the ED values are going to change as you get away from the wall. And you're going to get 2 sets of EDs. If you use the ED when the sun is out here, so the phi of the sun is 0, that means the sun is in front of the wall. Now this detector's in the sunlight. If you look at phi sun of 180, well, the sun's back here now, so somewhere here you're going to be in the shade of the wall, and then you'll come out into the sun. So if you plotted these ED values, here's ED versus the location of the detector. When it's in the sun, you're going to get some curve here, and then out here it'll agree with the hydrolyte value. And then for the values when it's in the shade, hopefully it'll be less, you'll get some value here, and then somewhere you come out of the shade of the reef wall, and then those values will go up and eventually agree with the hydrolyte values. So you get some feeling for things like, looking up, looking down, in the shade, in the sun, etc. And what I've been using this Monte Carlo code for is saying, well, if I have a detector here that was really measuring like E0D, but the detector's looking horizontally, what do those numbers look like for different water IOPs and all of that? And that's to improve the light calculations onto coral wall reefs to do better photosynthesis calculations and so on. So anyway, there's just some things like that you can play with here, and go to it, and I'll sit in the back of the room and await your questions. And then, for your presentations tomorrow, just whatever you cook up that you think is worth discussing or interesting or what you found, and, just I'll leave that to you.